What we are going today is, today I want to finish chapter 16. I think this should be possible. So essentially there are 4 sections left. One on parametric surfaces. The other one is then defining the surface integral. And then the 2 important theorems of Stokes and the Divergence Theorem. So essentially what we want to do is we want to generalize what we have discussed the last few times. So the last few times we mainly discussed results about vector fields in the plane, and now we want to generalize everything to the space. Just to remind you, if we have a 2-dimensional vector field, then we saw already that it's possible. It's quite easy. It's quite easy to determine whether such a 2-dimensional vector field is conservative or not. There is a very easy test. If xy is in some d and d is simple connected, which essentially means no holes, and open. So under these 2 assumptions, we have an easy criteria which tells us that f is conservative. So this can be written, there exists the f such that f is the gradient field of this vector if and only if we have this condition here. So the partial derivative of q with respect to x is equal to the partial derivative of p with respect to y for all xy in D. The proof of this result, in order to prove this, what we have discussed last time, so you have 2 directions. This direction here is Laurent's theorem, because what you essentially have here are the mixed partial derivatives, and they must be equal if f is a gradient vector field, because this means that the p is the partial derivative of f with respect to x, the q is the partial derivative of f with respect to y, and what you see here are the second partial derivatives. So from a mathematical point of view, this direction here, if f is conservative, proving that you have this condition here, it's just Laurent's theorem. And the other direction, we use Green's theorem in order to prove this, because if you look at Green's theorem, you see that on the right-hand side you have the difference of those 2 here, and once you have this condition, this means that the vector that the line integral along any closed path of f is equal to 0, and this is more or less equivalent to the vector field being conservative. Now, so this is the picture of conservative vector field. So in the plane, now we already saw a similar result for a 3-dimensional vector field. So if you have now the situation is not the same. So here it's not completely the same. Here we assume that the domain which we are looking at, even more general, is the whole space. But we saw already last time that there is a similar result which tells you that okay, so again, f is conservative. Okay, so if and only if. And this condition here is replaced by the curl of f is equal to 0. Okay, so the assumptions actually are different. Okay, so the situation is not completely the same. Okay, here you for this characterization you need that the vector field you consider the vector field on the whole space, whereas here you can allow that D is a subset of the plane, but you need those 2 assumptions here, simple connected and open. And here again, so the curl, of course you know that the definition of the curl is the del operator, vector product with the vector field. Now if you look at the curl, so one direction again is trivial, so proving from here to here is trivial. This is again just Clauron's theorem. But for the other direction, I just mentioned this result. I haven't proved it yet because for the other direction you need a generalization of Green's theorem, essentially to the space, essentially for three-dimensional vector fields. And I guess you know already from other classes that such an extension is provided by Stokes Theorem. Okay, so this is what I want to do today. So here, in order to prove this here, okay, the other direction, what we needed was, because you don't see line integrals here, but what we needed in order to go from here to here is the line integral. So we defined the line integral, and we figured out that for the line integral there is something like the fundamental theorem of calculus, so in other words, Green's theorem, and this helped us in order to prove this direction here. And here we will have something similar, so we have to define another type of integral, the so-called surface integral. And for this we have first to discuss surfaces. This concept actually is not very it's just a generalization of surfaces, which is quite natural, which is in the same flavor of parametric curves. So what we have is, okay, we have now a surface given as follows. So we have here coordinate functions. And UVs in some domain. So we can use such a vector function here. So for every UV in D, we get here a vector in this three-dimensional vector space. And as U and V is running through the surface D, what we get here traced out by the tips of the corresponding vector is a surface, and this is called a parametric surface. And for instance, if you fix one of those two here, of the two parameters, for instance, you fix V, and you consider this as a function of U, then what you get is a vector function. So this will describe a space curve, and such space curves, if you either fix V or either fix U, are sometimes called the grid of this parametric surface. So if you fix here V, or you fix U, these are sometimes called the so-called grid curves. Okay, so this is just you have a surface. So this will describe here as a surface. So actually, we identify the surface. Actually, this does not really describe a surface, but these are you have because this is a set of vectors. But the tips of the endpoints of the vectors give you a surface, and the grid curves are the curves which you see something like here, what a graving device like Maple would plot. Okay, now, so this seems to be quite natural to extend the notation of surfaces to such to include such more general surfaces. Now, of course, what we cannot do is we can for every point on the surface we can define a tangent plane. So what we are going to do is okay, so if you have a point here, then you just look at the corresponding two grid curves, and you look at the vector or the tangent vector to this curve here at this point, and to this curve at this point here, and the plane which is made up by those two is called the tangent plane of the parametric surface to this point here. So the tangent plane is the plane which is spanned by the the tangent vectors to the grid curves at a certain point. Okay, and you see that, of course, it's not the parametric surface has to be sufficiently smooth that you can define a tangent plane. What we do not want to have, so apart from those two vector functions must be differentiable, we also need that the vector product is not equal to 0. Because if the vector product is equal to 0, obviously it doesn't make sense to talk about the tangent plane. So we'll normally assume that a parametric surface for every point will satisfy this here, and such parametric surfaces would be called smooth parametric surfaces. Okay, so this is just an example, because we have just defined the tangent plane for a function of two variables, for the surface given by the plot of a function of two variables, and this is just an easy extension to more general surfaces, parametric surfaces. Okay, the next step is as for the, because we discussed already how to compute the surface area for certain surfaces, surfaces which are given by functions of two variables, and you can use a similar approach to define or compute the surface area of such a parametric surface. Surface area of a parametric surface. Okay, so we have given a parametric surface. Let's say UV in some domain, and for simplicity, we assume that the domain is just a rectangle. Okay, now what we are going to do is this is just the same idea which we have seen already before. So we are going to divide the domain into subdomains. So this is D here. We are going to divide it into subdomains. Then one of those rectangles, okay, you can lift it up onto the, using the defining equation, the parametric equations. You can take this and lift it up to the surface. So this will give you on the surface. Actually, this subdivision will give you a corresponding subdivision on the surface. Okay, and if you, for instance, take this subrectangle here, this corresponds to some part on the surface, on the parametric surface. Okay, and if you make now certain smoothness assumptions, you will see that this part here, so this area here, so denote the surface area of this part by, let's say, delta Aij, then you see that delta Aij will be given by, so what you do is you take this point here and you compute the cross product between the derivative of r at this point with the derivative of in both directions. Now if you, so this is kind of, because you can, this under certain assumptions, this kind of line will correspond to this one. Okay, so what you get here is in this point here the tangent vector to this curve here, and here in this direction, and what you roughly have, so this actually is roughly, is you lift this up and you compute on the area on the of this part here on the surface. Actually, we have done something very similar when we proved formula for the change of variables for a double integral or triple integral. So this is just the same here. So you see that we are going to define the surface area of this parametric surface, okay, as the double integral over our D, okay, and then you just sum over the lengths of those vectors here, of the cross product of RU with RV, and then you have a area integral. You have a double. You compute this double integral here, and this will be the definition. Or if you want to say, okay, this will be the way we can compute here the surface area. Okay, so actually we have defined already the surface area. For instance, for the special case where the surface is the graph of a function of two variables. If you are in the special case, so this would be an example. If you are in the special case where you have given a function of two variables and x, y is in D, and you have to compute the surface area of the part of the function which lies above D. So this was a special case which we have considered before, and if we look at this special case, then we should of course get the same result. Now this of course is true. So first you have to find the parametrization of this surface, but this is not complicated. You take just x and y as parameters, so you have here xi plus yj plus, and then this would be g of xyk. And so actually our parameters are now, our u and v are now x and y. Okay, so if we compute, so what we have to compute is this cross product here. So here we have I, here we have j, here we have k. Here we have this vector here. So the derivative of this with respect to x. So we have here 1, 0, and here the partial derivative of g with respect to x. And here the last row is the derivative with respect to y. So we have here 0, 1, the partial derivative of g with respect to y. So by the rule of computing the dot product here, what we get is minus I plus, this is actually a minus j, and the last one is k. So what we get is this here. So you see that in this special case, the length of this vector just becomes the square root of 1 plus, and then the partial derivative of g with respect to x squared plus the partial derivative of g with respect to y squared. Okay, and the new formula, or the way we have defined now the surface area, contains the old formula, because we proved previously that if we have a function of two variables and we want to find the surface area of this function of two variables above some surface t, then the formula which we have is, okay, the double integral over d, and then of this expression here, dA. So you see everything fits together. Not really a surprise, because that's the way it should be. Because essentially the way we derive this formula is just similar to the way we have derived this formula previously. So last time we defined the line integral for a function of two variables. Okay, so the line integral over some line, along some line c of this function f of x, y, ds, and this by definition, this was the limit. Okay, so n tends to infinity, and then we had the sum I from 1 to n, and then f evaluated at some points which we chose, some sample points, which we chose on the curve, and then multiplied with the length of the arc from, so what we had here is, so we had here some curve. We chose here some sample points, so P0, P1, P2, P3, and so on. Pn minus 1, Pn. So we divided first the curve into, so the curve is given by some parametric equations. Okay, so we divided the interval for the parameter, so let's say AB, into n subintervals, which corresponds then to these points here. And then in every subinterval, so, or in other words, if we are here on this piece here, we chose a point, a sample point, we evaluated the function at this sample point and multiplied it with the length, with the arc length from P0 to P1. And we summed up all those contributions, and in the limit, what we get by definition is the line integral. Now, we have a similar definition, or something similar to the line integral, now for a function of 3 variables. So now we have a function of 3 variables, and we have given here we had given a parametric curve. Now what we have given is a parametric surface. Actually, it's not really necessary that we have a parametric surface, so we can do even more general. So if you look, so assume we have given any surface S. Now, what we can do is, okay, we can divide this surface into subsurfaces. Of course, if the surface is not parametric, we have to say, okay, in which sense, but so maybe think about the parametric surface, but this can be done actually more general. And what we do now is, we just use a similar definition. So we define a surface integral over the surface S of this function here. S. Now the limit, now n and m tends to infinity, and we have now a double sum, I from 1 to n, sum j from 1 to m, and again we evaluate f at some point on the surface now. So for instance, you choose this point here. So if you look at this part here, okay, so what you choose is one point, a sample point inside this part here. And you multiply this with the area here of this part here. And then you sum over all those parts you see here and take the limit. So this is just the same as we have done here. And this integral is called the surface integral. Of f above S. Above over S. Of course, if the surface is a parametric surface, if S is a parametric surface, then from our formula for the surface area, what you would expect is that the ds here So formally, what you would expect is that ds is equal to the length of this vector here times dA. So what you expect would is that in this situation, the way you compute the surface integral is just as a double integral. You go over d, and then you just plug in. So the parametric surface is described by this vector function, and then you have here and of course if you have certain assumptions, I haven't said what the assumptions are. Of course you need here certain assumptions. You cannot allow all surfaces. You need even that this exists. You need here that the surface should be a good assumption is the surface should be smooth. The function should be at least continuous on the surface. And under this assumption, it's quite easy to prove that if you define the surface integral like this here, then for a parametric surface, the computation is just given here by this expression here. You see this. You find the explanation why as to why this is true in our textbook, but in our textbook you also do not have a real proof. Okay, this is just a rough explanation. Maybe a similar explanation you have seen already in other classes. A special case of this situation, a parametric surface is always the surface is the graph of a function of two variables. So if you have a function of two variables, okay, then the surface integral with graph S, then the surface integral over S of f of. So you see what you have to do is you have to plug in the let me first write it like this here. Now, so this means that the function has some domain, of course, and the way you can compute the surface integral by this formula is you integrate over the domain. You plug in a parametrization of the surface, which is given by x, y, and g of x, y, and you multiply by this here. We just computed it, so this is the square root of 1 plus the derivative of g with respect to x square plus the derivative of g with respect to y square, and then dA. So you can compute the surface integral by computing here this double integral. This also kind of gives you the relationship between the surface integral and the double integral. Now, the next step would be to extend the definition, because so far we certainly have to assume that the surface is a smooth surface, but actually it's enough if you assume that the surface is piecewise smooth, so you can decompose the surface into a finite number of smooth surfaces which make up the surface S, and then you define the surface integral over a piecewise smooth surface as the sum of the surface integrals. So if S is piecewise smooth, with, so this means you can decompose it into smooth surfaces. And SI smooth. And actually those surfaces, they just meet each other. The intersection is almost empty. They just meet each other at the boundary. So maybe the intersection of two of them just includes points on the boundary of those two. Then we are going to define the surface integral over such a S of f of x, y, z ds as the sum of the surface integrals. So this is actually the definition. Okay, so this is then the generalization of the surface integral. Now, I haven't really motivated why I'm interested in this object here. I guess you have seen this in other classes, so maybe you have enough motivation for this object from physics. But actually, the motivation for defining this object is pretty similar to the motivation we defined the line integral with respect to the arc lengths. Namely, for instance, if you have given a surface S and our function f of xy gives you the density of or at x, y, z. Okay, if you wanna compute the mass, what you need, of course, is the surface integral. So if you wanna compute the mass of S, then the mass will be given by the surface integral over S of this density function here. Okay, this is just motivated by the definition of the surface integral, because by the definition, what you do is, okay, you divide the surface S into subsurfaces, and you can assume that the subsurface is very small. And for this subsurface, what you do is, okay, you multiply the density with this area here, and you sum up over all of them. So what you get in the limit is the mass of this surface S here with this density function. Okay, so this is already one of the motivations for studying surface integrals. So you can use surface integrals to compute the mass of such a surface. You can also use the surface integral to compute the center of mass. You can define moments of inertia and so on and so forth. So it's a quite natural object in physics. Okay, so any questions to this? Now, the next thing which we want to do is, because the next step in the plane was to define a line integral for vector fields, so that's what we want to do here as well. And for this, we have to define what does it mean that the surface is oriented, and this is not very easy to define. So we're not really going to define it. We just briefly or roughly discuss what we mean. We do not give a precise mathematical definition, because this is not so easy. Okay, so if you have given a surface and you fix a point, then you see that in this point you have, if the surface is smooth enough, you have a normal vector, a unit normal vector. Not only one, you have two actually. So one pointing in this direction, and another one pointing in the other direction. Okay, so you have this, call this n here, and this minus n. So the unit normal vector. Now, a surface is called oriented if you can choose one of the twos, okay, in such a way that if you move over the surface, okay, if your point is moving over the surface, okay, the way the point is mapped onto n is continuous. So this is it's not a mathematical precise definition, but this is what it means that the surface is oriented. Now there are surfaces. If I give such a definition, it sounds like most of the surfaces actually are oriented, but you find in our textbook so-called Möbius strip an example for a surface which cannot be, which is not oriented. Okay, so but for us it's enough to think about. Okay, so you choose n. A surface is called oriented if you can choose n for every point, such that if you move along the surface, okay, then the way the point is mapped onto its n is continuous. Okay, so it's not that if you move suddenly you jump. For this surface, if you choose this n, you always have to choose this n which points in this direction. You also see that if a surface can be oriented, you have always two different orientations. Okay, the other you get one orientation here for this surface by choosing this n here, and another one by choosing minus n. Okay, so for instance, if you have a parametric surface, so if you have given, if this is a parametric surface, if S can be oriented, okay, if S is an oriented surface, then you have given a unit normal vector. You have a choice of a unit normal vector in the following way. You just choose this vector here. So this vector we know is because this vector is orthogonal to the tangent plane. So this is a unit vector, and you divide it by the length. Okay, and if you do this for the special case where the parametric surface is generated by a function of two variables. So for this special case, so in this special case, we always chose the vector function to be equal to then you see that this n here is given by, so I computed it before, so this is the partial derivative of g with respect to xi minus the partial derivative of g with respect to yj plus k over, and here you have this the square root of 1 plus the partial derivative of g with respect to x squared plus the partial derivative of g with respect to y squared. And you see that if you choose the normal vector, the unit normal vector like this here, then you see that the z coordinate is positive. So this orientation is normally called positive or upwards. So upward orientation. So let's say it's the equation x squared plus y squared plus z squared is equal to a squared, this surface. Now, of course, this is a parametric surface. It's easy to find the parametrization. You just use spherical coordinates. So a times sine of psi times cosine of theta. Y is a times sine of psi times sine of theta. And finally, z is equal to a times cosine of psi. So the parameters are psi and theta. If you now compute, this vector here, so u and v are now psi and theta. Then you can do this computation on your own. I have the computation here. So this is a square sine square psi cosine of theta I plus, and then you have a square sine square psi sine of theta j plus the last coordinate is a square times sine of psi cosine of psi k. of course, this the sphere, of course, can be oriented. From my not precise definition is quite apparent. Now you see, if you take this, because this is a parametric surface, so one possible choice of the unit of the normal unit of the unit normal vector is this one. What do I have here? So you see that we have to compute the length of this vector here. Now, if you square this, so you have you have to square all the coordinates and to add them and then the root. So if you do this for the first two, then because you have cosine square plus sine square is equal to 1, so what you have is a to the 4th, and then sine to the 4 psi plus, and you square this one, so a to the 4th, and sine psi square cosine psi square. So you see that this again simplifies, so we have here a square. You have to notice that if we use spherical coordinates, a is larger or equal than 0. So this is different from Cartesian from polar coordinates, where the radius can be negative as well. The psi is between 0 and pi, and theta is between 0 and 2 pi. You see that because what you have here is sine square of theta, so actually you have the, if you take the root, actually you have here the absolute value, but because we are in this range here, so the sign is positive, so we can forget about the absolute value. This is important now because for the orientation. Okay, so this means that this unit normal vector is given by. Okay, so you divide everything by this here. Then what you get is sine of psi cosine of theta I plus sine of psi sine of theta j plus, and the last one is cosine of psi k. And you see that actually this here, what is this? This is 1 over a square, 1 over a, and then the original. So you see that the unit normal vector here points in the same direction as the vector points which describes this sphere here. Okay, so this means if you look at the sphere, okay, then because the vector describing the sphere, if you look at this here, okay, points towards the sphere. Okay, and for every point on the sphere, the unit normal vector has the same direction. Okay, so it points outwards. Okay, so if you have the sphere, and for every point you choose the direction where the unit normal vector points outwards. Also this direction for a closed surface. Okay, this direction is called the positive direction or outward direction. Okay, because if you have a closed surface, okay, obviously you have two possible orientations of this surface. One is for every point you choose the normal vector which points away from this outwards, and one is which points towards the inside of the surface. Okay, and also this is called, as I said, the positive direction. Okay, now having this kind of notation, so the orientation of a surface, we can now define the surface integral of a vector field over an oriented surface. Okay, so assume we have a, so this is surface integral of a vector field So assume we have a vector. We have a three-dimensional vector field. And assume you have a surface S, which is oriented more or less. Oriented surface just means that there comes a unit normal vector with the surface, okay? And the unit normal vector, if the surface is parametric surface, okay, it's just given by the one I just showed you, okay? So with unit normal vector n. Now, the way we define the surface integral over S of the vector field. Now, since S is oriented, okay, I write for it like it's a vector. Okay, this doesn't mean money. Okay, this is this oriented surface. Okay, and the definition is okay. So what we do is we look at the surface integral we have just defined. We multiply f with this unit normal vector, which comes with the orientation ds. Now, I'm certain you know from physics what the meaning is of this kind of symbol. What is for us more important is how to compute it and how to use this kind of object to figure out, to prove that three-dimensional vector field is conservative if and only if the curl is equal to 0. Are there any questions so far? I guess most of this should be quite you should be quite familiar with this, because I guess you have learned this in other classes, and that's why I'm not going to spend time, and I'm not the right person anyway to give you a physical motivation why this symbol is important. But I guess you have seen this in physics, so you know this maybe much better than I do. Okay, so in order to talk about the surface integral of a three-dimensional vector field, okay, what we need is an oriented surface. Of course, the value of this symbol here will depend on the orientation of the surface. Now, let's look at some special cases. The first special case where our oriented surface is a parametric surface. So if S is a parametric surface, with unit normal vector so for oriented surface, for a parametric surface, if the parametric surface is oriented, we have a natural choice for the unit normal vector, namely what we choose is, as I have explained before, this one. Okay, there are two choices, okay, for the orientation. One would be this one, the other one would be minus n. Now, so in this setting, how to compute how to compute the surface integral over f of f over s. Okay, so we just by this definition here, what we do is, now for n we plug in this here, and for ds we can plug in. So ds was and then we integrate over d, where d is the parametric region, so the domain where the parametric surface is defined. Okay, and then what we have is f times, and we plug this in, and you see that this here cancels out. So what you have is this here. Okay, so this is the special case where we have parametric surface. Of course, in a more general case, you should read these kind of chapters in the textbook. You should be quite cautious in reading them, because in a more general case, okay, where S is not a parametric surface, we haven't really talked about, okay, how to find the n and so on and so forth. Okay, so actually, the textbook is quite precise in this for the case where you integrate over a parametric surface, but it's quite sloppy or foggy. The explanation is quite foggy for a more general situation. Okay, and if we even choose a more general, if we specify this situation even more, namely if our surface is given by a function of two variables, and we choose the orientation, so S is the graph of this of G. And we choose the orientation, what we call positive. Okay, so this means that that our RU times RV is equal to. So here, actually, the parameters are x and y. So I computed this before. So I have the partial derivative of G with respect to xi minus the partial derivative of G with respect to yj plus k. If the orientation would not be positive or outward, okay, we just have to replace this here by minus. Okay, then the surface integral becomes okay. So we have to compute this here. So the double integral over d. Now f has coordinates p, q, and r, and this here is the dot product. So what we have is minus p, the partial derivative of g with respect to x, minus q, the partial derivative of g with respect to y, plus r dA. Okay, so this is for the special case where the surface is given by the graph of a function, and the orientation is the positive orientation. In order to compute the double integral, if you have given such a function and you have given a surface, then you can use this in order to find the surface integral. Now, as I said at the beginning of the lecture, so what I'm interested in is a generalization of Green's theorem. Actually, there are two generalizations of Green's theorem, because we had two in vector notation. We had two forms of Green's theorem. The first form of Green's theorem in vector notation was, okay, you have the line integral over a closed curve of a vector function, and we write this as a double integral over the domain. So here for the curve you have of course the orientation. So C is the boundary of D, and we had here, so one of the forms was we had here the curl of f times k dA. Now we want to have something similar for the surface integral. So we want to replace this, or we want to replace this here by the surface integral. Okay, the surface integral over the curl of f, and here ds. Now this, as you know from other classes, I guess, is Stokes Theorem. So what do we have? We have a surface S, which we assume to be piecewise smooth. And oriented. Now, we assume that the boundary of S, so call the boundary of SC. So we assume that the boundary of S is simple piecewise smooth. And this I have to explain in a minute. Positive oriented, because now we are in the space. Okay, so this has to be explained in more details. Now, if we have a three-dimensional vector function, then you have something similar, namely, if you compute the line integral over C of the three-dimensional vector function dr, this will be equal to you have the surface integral over S of the curl of f, and then the S, where this here, because this is oriented. Okay, so you have to compare those two. So they more or less this here is an so actually this really is an analog of Green's theorem, namely if our surface, okay, is completely contained in the xy plane, okay, and you choose for the orientation, if we are in the xy plane, okay, the as the unit normal vector you choose k, then what you get exactly is this here. So actually this contains Green's theorem. Now the thing which I really have to explain is positive oriented. So what does this mean? Because we are now in the space, so we have a surface. So this is our S here, and this surface has an orientation. So with this surface comes a normal vector. Now the positive, you see that the boundary here, in this case, looks like it would satisfy this assumption: simple, closed, piecewise smooth. Now, how do I choose the orientation? Because here for the line integral, I need the orientation. So again, if I walk, I choose the orientation such that if I walk along the boundary, okay, and I stretch out my left hand, okay, then my left hand is pointing inside the region, okay. But of course, I have two ways I can walk. I can walk like this, or I can walk the other way around, okay. So what I assume in addition is that my head is pointing in direction of the unit normal vector, okay. So I walk here. I walk like upside, okay. If you look at the surface like I've drawn it, okay, the part. Okay, so the orientation will be this one, and this one will be called positive. Okay, because so once more with the surface S, there comes already an orientation. So for every point you have a normal vector. Now this orientation will induce orientation for C. Okay, namely you walk at the boundary such that your head is pointing in the same direction as the unit normal vector. So that's how you stand on the surface, okay. And if you stretch out your left hand, then your left hand will point inside the region. Okay, so I guess you have seen this result already in other classes. I'm not sure whether you have seen the proof of this result. Yes or no? You have seen this result, right, in other class, physics. It was proved there or not? Actually, I would be surprised if they had proved it in full generality, because the proof in full generality complicated. Okay, it's not easy, but it's not so complicated to prove the result if you look at, in particular, special surfaces. Okay, because if you look at a very general situation where S is any piecewise smooth oriented curve, oriented surface, okay, and with the boundary being simple, closed, piecewise smooth, and having this orientation, this is complicated to prove. Okay, in particular because we haven't even explained properly in mathematical language, okay, what it means that the surface is oriented. Okay, we haven't defined it. So but in the special situation where, for instance, the surface here is given by the graph of a function, and you make some further assumptions, this is not so complicated to prove. So let me. So for the proof, so I just show you how to prove it for us in a special situation. Okay. So what I assume is that I just consider special surfaces, namely surfaces which are coming from a function of two variables. So I have a function of two variables, and S is the surface. So S is the graph of G, and as orientation, I choose positive, the positive orientation or upward orientation. Okay, so maybe it's worthwhile to. Okay, so I have something like this here. Okay, so this is our this is the graph of our function. Now, actually, I have some. So here I have the domain of our function. So this is D here. Okay, so our xy is in D. And the orientation I choose is the one with the positive. So I choose the, in every point, okay, I choose the normal vector which has a positive set coordinate. So that's why upwards. Okay, if I draw things like this here, then the orientation is upward. Moreover, actually, I need some more assumptions because you see that for this choice here, you see that C here will be oriented like this here. So this is C here. Now here you have C1. Now, of course, it's not necessary that the boundary here corresponds to the boundary here. Okay, this depends on how the function maps. How D is lifted on the surface, okay? But I assume that the boundary here, okay, is under the function G is mapped on the boundary here, okay? And I assume that I have that the parametric description of C1 is given by, let's say, x is equal to x of t and y is equal to y of t. Okay, where t is, let's say, between some a and some b. So this is a parametrization of C1. Now, if I look at this special situation, okay, the proof is not so complicated. It's just computation. So I just compute this here and I compute this here. Okay, and I show that they are the same. You will see that actually, because I said that this is really a generalization of Green's theorem because it contains Green's theorem, but you will see that this doesn't mean we can just prove this and then deduce Green's theorem from it, because the proof which I show you will use Green's theorem. The curl of f times ds. Now, for such special surfaces, okay, I have computed. I have shown you how to compute this surface integral just before. So this is you can compute this as a double integral over d. Okay, and then you have the components of the curl of f. I don't remember. and here you have we have P, Q, and R. Okay, so you just choose the form. You just use the formula I showed you before. Minus the first one is the P coordinate of this vector field here. So what you have is the partial derivative of R with respect to Y minus the partial derivative of Q with respect to Z, and then multiplied with the partial derivative of G with respect to X minus. Now, how do I? Because I need to keep some of the. So this I will keep here. Now this one is now Q. So Q is the partial derivative of P minus, because you have a minus, so I. And the last one is plus here, and you have the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y dA. Okay, but actually, yeah, okay. But actually here, I should say you have x, your z coordinates becomes g of xy. Okay, this is what you plug in. Okay, so this was the right-hand side of Stokes theorem, and I just have to show that the left-hand side is the same. Okay, so what was the left-hand side? So the left-hand side is the integral, the line integral over c, and then f times dr. Now you see that if I choose this orientation for C1, then you see that parametrization of C would be given as R of t is equal to. So I have here also x of t. I have here y of t, and the last one is then g of x of t, y of t. Okay, so. And we assume that f, this we have already here, so f has the component fields p, q, and r. So what we have here is the integral. Now t goes from a to b, and f is pi plus qj plus rk times, and here I have to multiply with the derivative here of this one. So I have here the dx over dt I plus dy over dt j plus, and for the last coordinate I have to use the chain rule. So I have the derivative of g with respect to x times the derivative of x with respect to t, and here I plus the derivative of g with respect to y times the derivative of y with respect to t k. Okay, so we actually I don't need this picture anymore, but I need this here. Okay, now the rest is just computation. Okay, so this is the dot product. So what we have is the integral from a to p, then p times plus, and then I should maybe order this already, or let's maybe first do q times. And then this here times r. Now, okay, so now what I want to do is I want to order this. So I want to group things which have partial derivative of x with respect to t I want to group those things together, and I want to group things which have the partial derivative of y with respect to t together. Okay, so you see that this is equal to what? This is equal to p plus, and here I have r times the partial derivative of g with respect to x, and then I have the partial derivative of x. Actually, those partial derivatives are actually just normal derivatives. Plus, and here I have the other one. So the other one is q plus r times the partial derivative of g with respect to y and this is the partial derivative of y with respect to t. Now you see that this, what you see here, you can write this as a line integral, okay? Because this is the line integral over now C1, okay? Now we are down to the xy plane, and maybe I write here some vector function, but this is a two-dimensional vector function now. Times, okay, where our this here has this and this component vector field. So p plus r and q plus r times. And here I can now apply Green's theorem, okay? Because you see that the orientation is also the right one. So meaning that if I look at this d here, okay, then C1 is the boundary of this d, and is already oriented in the right direction, okay, in order to use Green's theorem. So by Green's theorem, now I can erase this. By Green's theorem, this will be equal to the double integral over d. You see, I get something similar to this here. This is my idea. Okay, the double integral over d, and then I have this here with respect to x. So minus. And this here with respect to y. And what do I have here? P plus r. Okay, that's wonderful. Now, maybe it's not really, it's not obvious yet that this is equal to this here, right? I guess nobody can see this now at the moment. But you have to keep into mind that Q has, every of the component vector fields has 3 coordinates, okay? And the first one is x, the second one is y, the last one is g of xy. So if you do the partial derivative here, okay, you have to use the chain rule for this one, okay? And also for here, okay? So actually you get here many terms. Okay, so maybe because of time. Okay, so now the only thing you have to do is you have to rearrange this here, and you will see rather quickly that this is equal to this one. Okay, so what I still have to compute is this partial derivative here, and you have to be careful. The partial derivative of q with respect to x. Okay, this is not just this is not just this term here. Okay, this would be the partial derivative of q with respect to x plus the partial derivative of q with respect to z times the partial derivative of z, which is q, with respect to x. Okay, you have to be careful here. So for this one, and for this one you have to be careful, and so on. But so you get here many terms if you compute here this partial derivative and this one, and then eventually you see that some of them cancel, and the remaining one you can rearrange them so that you get this here. Okay, so you see for this special case, okay, the special case I considered Stokes Theorem is not complicated to prove. It's just It's just you take the left-hand side, you compute it. You take the right-hand side, you compute it. Okay, and you compare that those two sides are the same. I just wanna point out that, for instance, if you take the partial derivative of this q here, okay, you have to be careful because q is actually a function which is like this here. Okay, so this partial, because you might easily forget here you have twice x. Okay, once here and once here. So this actually is this partial derivative plus, and then the partial derivative of q with respect to the last coordinate, and then because by chain rule. So it's like, because the only thing I want to point out is that this is not because you know why this is wrong. You understand why this is wrong. Because this is just a partial derivative with respect to this. Actually, the x has here a double meaning. Okay, x is the parameter, but x, you would think x is also the variable here, the first variable. But so x has a double meaning. That's why. Okay, so you see that Stokes theorem if the surface is given by the plot of a function, by the graph of a function, and the orientation is the positive orientation, and you have some additional assumptions which I just stated, then Stokes theorem is not too complicated to prove. It's just straightforward computation. But of course, you need Green's theorem as an input. Now, maybe once more Stokes theorem. Is equal to the double integral over c and f times dr. Okay, so once more. So from a physical point of view, I guess you have seen in other classes many the applications of this theorem, so you know how to interpret this theorem from the point of view of physicist or engineer. For a mathematician, what does this theorem say? This theorem is actually another extension of the fundamental theorem of calculus to higher dimensions, as Green's theorem was. Namely, because the curl is something like which involves partial derivatives. So this is kind of some kind of derivative of f. Okay. So what you have here is the integral of a derivative, and Stokes theorem tells you, okay, that in order to evaluate this integral, the integral over derivative, the only thing what you have to do is you look at the original function, okay, of the antiderivative. So kind of this is the antiderivative, and only the behavior of the antiderivative at the boundary is important. Okay, so this is somehow similar to this here. Okay, so here you see as well, you have the derivative of a function and the integral. Okay, you want to integrate it. What you do is you take the antiderivative of this function and evaluate it at the boundary. And the same here. The curl is a kind of derivative of the vector field. And the way you can compute it is you find the antiderivative, which is f itself, like here f, and just the behavior of the antiderivative at the boundary is important to evaluate the surface integral. So this would be a kind of analog of the fundamental theorem of calculus for surface integrals. Okay, so that's the first thing. My time is. The second thing is you can use Stokes theorem to prove that f is conservative, so there exists an f such that if and only if the curl of f is equal to 0. Last time we already saw that this here is equivalent to the line integral over any closed path is equal to 0. Okay. So last time I discussed this. Actually, last time I just discussed those things for in the plane. Okay, but some parts I discussed last time. Okay, are not so straightforward to extend to the space like Green's theorem we saw. But last time we also saw a fundamental theorem of calculus for line integrals. These, of course, last time I just proved it for the plane, but you can take the same proof and you can prove it for the space as well. Okay. Similar, you have a vector field is conservative if and only if three-dimensional vector field is conservative if and only if the line integral for every closed curve is equal to 0. But you need some you need some assumptions on the domain of f, namely the assumptions what you need is that the domain is open and connected. Connected you certainly need because you want to connect 2 points. Okay, so this is this here. Now, for this here, okay, I already showed you, or I already told you at the beginning of the lecture that this direction is trivial, almost trivial, because this is just Clauron's theorem. Now, for the other direction, okay, if you know that the curl is equal to 0, okay, now what you want to show is this one, because this is equivalent to this one. Okay, so you take a closed curve. Let's first assume this curve is not only closed but also simple closed. The difference to remind you between closed curves and simple closed curves is that a simple closed curve does not cross itself, whereas a closed curve might cross itself. But this doesn't really matter because if the curve is crossing itself, you decompose it into two curves, and both of them are simple. Okay, so if you have this here, okay, then you what we want to show is this one. So we take a closed simple curve. Now you see, if you apply this one, the curl is equal to 0, then you see that this integral is equal to 0 and you are here. Okay, so this argument is pretty convincing. The only thing which you have to do is, and this is not non-trivial, this is not so easy, is to show, okay, you can find, because you have given C here, okay, with an orientation, and you have to show that, okay, it's possible to construct a surface which you can orient in such a way that the induced orientation of C is the orientation you already have here. Okay, so if you want to apply this, what you have to do first is, because you have a simple closed curve, you want to prove this here. You have to show that you can construct a surface S which satisfies the assumptions of Stokes Theorem, okay, such that the boundary, okay, with the induced orientation of the orientation of S is your C. You have to construct this, and then you just apply it, and that's it. This the main complicated part in proving that this is equivalent here is in construction of S. Okay, and I showed you that this result, okay, in general is just true. For instance, if you assume that your domain is the whole space, okay, because under this assumption it's not so complicated to construct S. But if your domain here is restricted, okay, it might be more complicated to construct your S. So this is just to show you where the real difficulties are in proving this kind of result here, and how this is interrelated to Stokes theorem. Namely, actually, of Green's theorem in vector notation, we had two different versions. First one, so this is once more Green's theorem. One version was okay, that the curve, the line integral, f is always two-dimensional, of a two-dimensional vector field is equal to okay, the double integral over d, and then you have the curl of f times k dA. So this was one version. Another version was that the line integral over c of f times n ds is equal to, and again you have the double integral over d, but now you have the divergence of f dA, where the divergence is the derivative of p with respect to x plus the derivative of q with respect to y. Now, you would, from this result, you might have the idea, okay, that I replace this here by a surface integral, because the surface integral of a vector field was defined by the vector field times the unit normal vector, and then here d, but capital S, and this here you replace by triple integral, and this in fact is true, and is called the Divergence Theorem. But we need some assumptions now. What we have given now, so in this situation, what you have given is a plane region, okay, and this is the boundary. Now what we have is space region, and the surface, which is the boundary of the space region. Okay. Now for the space region, we cannot allow any space regions. It's like here for D, we couldn't allow anything because D in the most simplest form of Green's theorem, okay, does not have any holes, simple connected, okay. So here is similar, okay. So we define so-called simple, or we introduce so-called simple plane regions, space regions. Now you can think about simple space regions, simple solids, space regions which, because we previously, when we discussed triple integrals, we talked about space regions of type 1, type 2, and type 3. Type 1 was is kind of like a cylinder. So a space region of type 1 was you had a plane region, okay, and then you have two functions, and you say the cylinder, which is given by so you look at all lines which pass through the plane region, okay, and are between two function values. This is a space region of type 1, and similar type 2, type 3. Now what a simple space region means, okay, it is simultaneously of type 1, type 2, and type 3. Okay, you can think about a simple space region like this. So this means it's kind of this is a space region, okay, where no matter how, if you look in z direction, okay, so you have two boundaries which you can describe by a function of two variables. If you look in y direction, you have two faces which you can describe by a function of two variables, and the same in the x direction, roughly speaking, okay. For simplicity, you can just think about the box, okay? So E, for instance, a box. Now, let's denote by S the boundary of E. E is a solid, okay? Something which is closed. So the boundary is something which is a closed surface. Okay, and for a closed surface, you have two orientations. One is away from the surface. One is inside the surface, positive and negative. So because we want to replace this here by the surface integral. Okay, so we have to choose orientation of S. We choose the positive orientation with positive orientation. Then you have the following. So the surface integral over S of f times ds. So maybe I write this in the same form, that because this is the definition of the surface integral of a vector field is equal to the triple integral over E of the divergence of f dv. Okay, so this is an extension of the second version of Green's theorem to surface integrals. Now, again, for a mathematician, you can interpret this once more as some kind of a fundamental theorem of calculus now for trivial integrals. Because you see that the divergence, okay, so maybe I write. You see that divergence is some kind of derivative, okay, a derivative of f. And this result tells you, okay, that the triple integral of this kind of derivative is you can compute the triple integral, okay, by doing what? Finding the antiderivative, which is f, and the integral just depends on the values of the antiderivative of this here, so of f on the boundary. Okay, the boundary is S. So you see, this is another. As Green's integral can be interpreted as a version of the fundamental theorem of calculus for double integrals. This can be interpreted as a version of the fundamental theorem of calculus for triple integrals, and this is a version of the fundamental theorem of calculus for surface integrals. Okay, so. Just to summarize, you have seen this result, I guess, in classes on physics and engineering. So the Green's theorem, Stokes theorem, and the divergence theorem. But from a mathematical point of view, all those results are just higher dimensional versions of the fundamental theorem of calculus. Once more, the Green's theorem is a higher dimensional, is a version of the fundamental theorem of calculus for double integrals. The divergence theorem is a version of the fundamental theorem of calculus for triple integrals, and Stokes theorem is a version of the fundamental theorem of calculus for surface integrals. This here, the proof of the divergence theorem, you can find it in our textbook under this simple assumption. It's not so complicated to prove. This is not so hard to prove than Stokes theorem under the most general assumptions. And finally, if you are interested in this kind of, if you want to understand this kind of results in more details and generalizations to higher dimensions, then in particular, this is in general true if you are interested in learning calculus in much more details. We have a course on higher calculus, which where you will essentially start once more. So essentially, you will once more learn things about sequences, things about series, and so on. Because at this stage, we are kind of facing again the same problem which we have faced at the beginning of this year. Namely, at the beginning of this year, you have learned already many of those things in high school, but not precise enough. So we spent quite a lot of time to making things more precise, but as we went on, things were getting more and more sloppy, and actually they are too sloppy now in order to go on. So if you really want to understand this kind of stuff in much more details, you should go to higher calculus, where you will have to learn the same things once more. So you start once more from the beginning, you learn once more the epsilon delta definition of the limit and everything. Okay, so any questions? This is just to say that calculus is not over with this course. There is much more to learn about calculus, and you will certainly have other classes where you learn similar things, but from another angle.